Okay, whenever you're ready.
Okay. Hey everyone. So my name is Rachel Balgi and I'm currently a sophomore studying electrical engineering. Today I just wanted to go over a little bit more about sensors and how we could implement them into our own embedded system, whether that's just small designs or robots. So yeah. Quick little intro about me. Again, I'm studying electrical engineering and I am potentially minoring in computer science. I joined robotics this year, but I have not had the chance to really come to any meetings because I do have classes on Monday. So I'm thankful that I'm here today. Over the past summer, I worked with embedded systems a lot. So I was working with STM32 Nucleo boards, LCDs, oscilloscopes, 3D printing, and just kind of playing around with them, seeing how I could implement them into some bigger design. And I started focusing a lot on sensors last month. So kind of wanted to teach you guys about what I've learned so far. And some of my hobbies are just snowboarding and I love health and fitness. Okay, so I wanted to go over what an embedded system is briefly because I know a lot of people don't really know the exact definition of what it is. So first I want to talk about the IoT effect, which is basically when you have an embedded system, but it's connected to the internet. So you're able to share data through the cloud using Zigbee, Wi-Fi, or Bluetooth. And it's so important for companies because it gives them the opportunity to, I guess, analyze a product and see how the user interface experience is going, and allows the transfer of data to be so much faster, and it costs lower than if you were to not have the IoT effect. So yeah, again, everything is connected and you have smarter, more responsive technology. An example of this is when you can turn on lights in the room using your phone, or when you can enable the house alarm using some type of app. And it allows for a shorter development cycle. So you can update the software through the cloud, instead of having inflexible software where it would be harder to debug or just fix any minor errors. And again, it's just leading to enhanced user experience. And in this case, sensors, they could help transmit data from products to companies, as I said before. And we could have interactive sensors, which I'm going to talk about later, and how you could implement them into robots. And yeah. So I also wanted to talk about what things you should consider when developing any type of embedded system. These are the, I guess, surface ideas. So you always want to consider some type of RAM or memory and the code space. And one thing that I wanted to know is that anytime you're considering ROM or flash, you always want flexible code because any system, it's always going to have a specific purpose for an application. So you want to make sure that the system can support any changes. And going off of that, there's an idea of encapsulation, which is basically when you bundle data together, and it inhibits you from, I guess, altering the code as a whole. So you could change minor details in your code, and it wouldn't affect the software negatively. You also want to consider any processor peripherals. So in this case, input, outputs, sensors, display. You want to think about the processor cycles, the speed, and also the power consumption. And a good thing to consider is that some of these are tradable in a sense where you can increase one in order to optimize the other. So in the case that I put, you can make the software run faster, so you can increase the processor speed by putting in more code space, so more flash or more ROM. Okay, so a little intro to sensors. I'm going to use the example of a flow rate detector just to explain the difference between a macro and a micro sensor. So first we have macro sensors, and they basically just measure any type of movement, or in this case, flow rate at a macro level. So if you look at the two pictures, the one on the left is a ventometer, and that basically measures the flow rate of any type of liquid in a pipe. And then the one on the right just measures the movement of gas. So when you're working with macro sensors, you always want to consider that it's going to have moving parts, and those moving parts, they may interfere with the fluid flow and thus the sensitivity. But on the other hand, when you have micro sensors, they are so much easier because, again, you don't need any removable parts as you would for macro sensors. And they're so much easier to manufacture and implement into your system. And that would be easiest in our case when we're talking with robots or just smaller designs. And the technical word for this is MEMS, which just stands for micro electromechanical system. And that's basically when you can reduce the size of any type of sensor in order to implement them into your system and allow for a higher sensitivity to the flow rate in this case, or allow for lower power consumption. And my experience with a microsensor over the summer, I actually worked with one where it was so much easier to prototype in the embedded system that I was working with. So I was able to 3D print like a small casing for it. And I saw how it was able to interact with other components during like the prototyping stage. So yeah, that was just my experience with microsensor. Okay, so the first type of sensor that I wanted to talk about is an ultrasonic sensor. And there's two different types. There's one that's called time of flight, and then there's another one called the Doppler sensor. And they're pretty similar, but they're different in the sense when you're talking about like manufacturing and also the cost, which is really big and important to consider if you're mass producing any type of system or design. But a time of flight sensor, which is the image on the left, basically emits waves in short pulses, and it hits the object that you're trying to detect, and then it reflects back. And the time that it takes to reflect back is used to determine the distance from the object. So let's say you are trying to determine, you have like a small device and you want to know how far you are from a certain building. Obviously, you would need a very highly sensitive sensor for that, or time of flight sensor for that. But just as an overall example, you could use a time of flight sensor for that, because again, looking at the picture on the right, it would emit those waves and it would use a small formula to determine the distance. And in our case, it could actually help a robot navigate. An example of this would be an anti-collision system, in a sense where the robot will be able to recognize its environment around it. So when you use a time of flight sensor, it could tell the robot if there's something in front of it or while it's moving, I guess to avoid any type of collision. And then a Doppler sensor is also pretty similar to a time of flight sensor, but it uses a different equation, and it could also detect the flow velocity by determining the Doppler frequency, angle, and using the speed of light in the formula. And again, like I said before, the Doppler sensor is a little bit more expensive than the time of flight. So it would be pretty important to consider what type of design you need and whether you are mass producing your system or not. Okay, so another type of sensor is an accelerometer. And this basically measures the acceleration of a body in all different axes. So as you see in the image on the right, that is an accelerometer from SparkFun, and it is able to measure where the object is moving on the X, Y, and Z plane. And the way that it works is that it has different capacitative plates inside of it, and some are stationary, but some are also moving, and they move because of the forces that are acting on it. So as they move, it causes a change in capacitance, and from that, it's able to detect the change in velocity, which we all know a change in velocity is acceleration. And I also wanted to note that you could also get an accelerometer that revolves around a piezoelectric material, which is basically crystal or ceramic. And what that is that, as you see on the picture on the bottom, if there's some type of tension or stress that's applied to the material, it causes an electric charge. So on the right-hand side, you see a voltage meter, and when the spring mass is pressed down onto the material, the arrows will fly to the right because there will be a voltage difference. So yeah. Okay, so another type of sensor is an IMU sensor, and this has different components. It's more so a combined sensor of different types of sensors. So at the bottom, I stated how it's created from an accelerometer, gyroscope, and magnetometer. I'm not sure how to pronounce that, apologies. And it basically senses how an object is moving and its orientation. So it could sense when the object is tilting, when it's rolling, and again, just like the accelerometer, it senses where the direction of the pin is facing based on the coordinate plane in the X, Y, and Z direction. An example of this would be the BMI 270. And we see this used a lot in GPSs when the airplanes are flying in a mode where the captain is putting on like autopilot, headlights, and any type of like target achievement, which we will see later. I put in a little example later on. And this video is just a quick 2-minute, I guess, depiction of these 3 sensors and how they're composed.
Something irresistible, something very, very hot.
First, let's briefly explain how each of these microelectronic
Can you hear it?
Yeah.
Awesome.
mechanical systems or MEMS sensor work. We will start with the accelerometer. It measures acceleration by measuring change in capacitance. Its microstructure looks something like this. It has a mass attached to a spring, which is confined to move along one direction and fixed outer plates. So when an acceleration in the particular direction will be applied, the mass will move and the capacitance between the plates and the mass will change. This change in capacitance will be measured, processed, and it will correspond to a particular acceleration value. Next is the gyroscope, which measures angular rate using the Coriolis effect when a mass is moving in a particular direction with a particular velocity, and when an external angular rate will be applied, as shown with the green arrow, a force will occur, as shown with the blue arrow, which will cause perpendicular displacement of the mass. So, similar to the accelerometer, this displacement will cause change in capacitance, which will be measured, processed, and it will correspond to a particular angular rate. The microstructure of the gyroscope looks something like this: a mass that is constantly moving or oscillating, and when an external angular rate will be applied, a flexible part of the mass will move and make the perpendicular displacement. Okay, now let's explain how the magnetometer works. It measures the Earth magnetic field by using Hall effect or magnetoresistive effect. Actually, almost 90% of the sensors on the market use the Hall effect, and here's how it works. If we have a conductive plate like this and we set current to flow through it, the electrons would flow straight from one to the other side of the plate. Now, if we bring some magnetic field near the plate, we would disturb the straight flow and the electrons would deflect to one side of the plate and the positive poles to the other side of the plate. This means that if we put a meter now between these two sides, we will get some voltage which depends from the magnetic field strength and its direction. The other 10% of the sensors on the market use the magnetoresistive effect. These sensors use materials that are sensitive to magnetic field, usually composed of iron and nickel. So when these materials are exposed to magnetic field,
I love how that video just ended, like mid-explanation.
Yeah, I know. I think it was supposed to go more in depth. And I don't know what happened. I'm pretty sure there's a part 2 though.
But that was good. That was what you meant to show.
Yes.
Awesome. Okay.
Okay, so I also wanted to recommend a development board if you guys wanted to try it out. I tried this one out back in the beginning of September, and it was really cool. So it's basically a gesture sensor, and it also senses not just your movement around it, but also the temperature and if there's any heat or like flame being, I guess, applied around it. And it's really cool in the sense where you actually have like all the results on your phone, which is what we talked about in the beginning with the IoT effect. So there's an app for it and you could see everything through that. And also, I'm not sure if any of you guys have watched the channel Stuff Made Here, but there's this quick video about an automatic pool stick, and he does use a couple of sensors in it. So I wanted to show you guys just a quick 5-minute video. I thought it was really cool in his own design. But yeah.
All we need.
I cannot skip this ad.
Full-time, part-time, in or out of uniform. How many moments can you give?
N2E Robotics is not sponsored by the Air Force or Marvel.
It'd be pretty cool if we were, though.
It would be.
Come on.
21 minutes long, but we could go up until
You're the
5
best
minutes.
loser that I know.
Instead of being a loser that's somehow a winner, let's actually win.
I don't have skill, but I do have technology. So let's be honest, robots are better than us. They're more precise, great at computation, and they work long hours for no pay. I'm going to apply these strengths to pool to make a robot that will find and take shots that humans could only dream of. I'll also be using this robot for something that you might not expect. I'm going to use it to play pool online physically, which raises some pretty interesting ethical questions.
It definitely doesn't seem like it's working.
This was kind of a random idea, but turned out to be really fun. This just might be the star of the whole show. Playing pool takes skill, for now at least. It's also a game with many variants. I'm going to be focusing on 8-ball pool. 2 players take turns trying to sink all their balls by striking a white cue ball with a stick. The gameplay boils down to 2 steps. Figure out what shot you want to take, and then hit the balls very precisely to execute it. I want the robot to do both of these things. Figuring out what shot to take, henceforth referred to as the big brain algorithm, is going to take some explaining, and I'll get to that in a minute. The idea behind the robot is a bit more straightforward. Say I'm trying to make this shot. If I had a robot in the tip of this cue, it could move the tip so that it hits in just the right way so that the ball goes in. Here's what we're going to have to build. A camera system to watch the game and figure out what's going on, a complicated algorithm to interpret this and figure out the best shot, and a pull cue with a magic robotic tip that can take the shot for us. This is probably the most complex project that I've done. The robot cue is obviously going to have to move and rotate laterally, but pull is not 2D. Where you hit the ball vertically matters a lot. Off-center hits put spin on the ball, which gives you control over where it goes. I want the robot to have control. That means moving and rotating vertically as well. Fitting a mechanism that can do all these motions into the tip of a pull cue is going to be very hard. It's going to get fat, but my goal is for it to at least remain a stick. I have an initial design, but I don't have a good feel for it. I need to hold it. I haven't really talked about my Glowforge, but it's really useful for making quick prototypes like this. I use it kind of like my plasma cutter, where I can very quickly make structures out of flat patterns, except for in this case, out of plastic and wood rather than metal. I'm glad I quickly prototyped this because there's no way this is going to work. It's just too bulky and there's no way I'm going to be able to get this stiff enough. Deep down, I knew that a Stewart platform was probably the right way to go here, but I've done everything I can to suppress that thought because I know it's going to be very painful to make. The idea is that you arrange 6 telescoping rods in a very special arrangement. You can completely control how this platform moves around by extending and contracting these rods. I can stick a tiny one of these in the queue to move it wherever I want. It's very stiff, so it won't deflect when I take a shot, and it's also really compact. I wanted to avoid a Stewart platform because there's a ton of finicky little parts. Instead of telescopic rods, I have the linkages on these cranks, which push them up and pull them down, but it's essentially the same. The defining feature of this Stewart platform is that it's driven remotely through tension cables. The servos are on one side of this broomstick, and the moving end is on the other. The electronics are pretty straightforward. They're mostly off-the-shelf microcontrollers and other components. Man, that end got thick. Not really the best look. There we go. These platforms take a bit of math to move them around, but it's really not too bad. Say I wanted this platform to move over and rotate like this. One of the actuators gets shorter, 2 get longer, and it results in it being in this position. If I want to calculate how long these actuators need to be, I have the solution right here in front of me. This is how long they need to be for it to go here. Conceptually, all I have to do is move the platform where I want it and then measure the distance between these sets of points to tell me how long each actuator needs to be. I solved it by drawing a picture, but it's also very easy to solve this mathematically using linear algebra. That is exactly what my program is doing. This is a case where the results make it look much harder than it actually is. If I did everything right, the platform should move wherever I want now. Wow, working on the first try is not normal. It's pretty cool how the motions all combine, isn't it?
Mood.
This air cylinder on the tip of the cue will be used to fire the shot. It's connected to pressurized air, and when I open a valve, it shoots out really fast. But not all shots are done at maximum power. We need a way to vary the power from gentle touch to battering ram. To do this, I built the power pack. This tank is normally intended for car horns. The tank has a small, wimpy computer attached to it, which people call a microcontroller. The microcontroller measures the pressure with this pressure gauge. If the pressure is too low, it'll open this valve, which will connect it to my shop air and pressurize the tank. If it's too high, it'll open this valve and release the pressure. And to fire, I open this valve. It's really simple and works well. This cue is really cool, but it's completely useless without some more information. If I'm holding it here, how does the computer know that it needs to move it over here so the shot will go in? I have to know where everything is to be able to figure that out. I have this camera mounted on the ceiling looking straight down. It can see everything going on the pool table. It has a big problem though. Although this table was the cheapest one that money can buy, it is not this out of square. This image makes the balls look like they're over here, but in reality, they're over here. This is caused by the camera being out of square with the table. If I took the position of the balls from this image, then I'm going to calculate the wrong thing. Programmers call this garbage in, garbage out. I've heard this also applies to raising children. I glued these funny looking tags to all the corners of the table, and they're called fiducials. They're basically a reference point that's very easy for a computer to pick out of an image, kind of like a QR code. I can find these 4 points and then use them to straighten the image up. I know where the holes and bumpers are relative to the fiducials, so I know where they are now too. And then if I find...
As a vision person, I was like, oh my God.
That's
Yeah,
pretty cool.
Yeah, it's really neat. If you guys have like more time on your hands later on, I highly recommend watching that video. And also he has like really cool and like unique videos with like robots on his channel. So yeah, I also wanted to recommend 2 books that I read over the summer, and it allowed me to gain so much knowledge about embedded systems and just working with different peripherals, whether that's sensors, displays, external memory, and just managing the flow of activity and allowing me to learn how functionality in your system is so important and how you can optimize it. So yeah, if you guys are interested, highly recommend these books, and that's about it.
Thanks. All right. I'm trying to figure out how to full screen. Okay. I guess with that, do we have any questions, comments, concerns? I had one regarding this slide.
Mhm.
No, not that slide. This slide? No. Which slide was it? This one. Okay. What is ROM?
ROM is read-only memory.
Right.
Yeah, I sometimes I mix that up with RAM. Just
I'm sitting here like RAM. This is an O though. Okay. Cool.
Yeah.
Okay. I'm gonna stop sharing and also stop recording.